CHEM115 And then
All right, look, a few of you are here. 21 of you are here. Andrew,
How's it going?
not bad on yourself.
It's going. So not really doing much. Just trying to keep up with everything and then trying to make sure that my grandma doesn't go out and all that stuff. So
I get it. I totally get it. Is she staying healthy? You guys getting everything you need?
yeah, for the most part, we haven't in Yorba Linda. There hasn't been any reported cases.
Okay.
So far, like that's a plus. But she's been just walking outside and stuff. She used to volunteer at a like assisted living place. She can't do that anymore. So keeping her busy is what's like important. So she stays like up and stuff and doesn't start getting like, sad or anything like that.
How old is she?
82.
Okay, so that's up there. That's
Yeah.
up there.
Did you guys know that we're winning now?
Yeah. I wouldn't necessarily call it winning, but yeah.
We're wedding now?
We're number one.
We're
in the world.
winning. We're number one in like cases of
Oh, I
coronavirus more
see.
than any other country.
The U.S.?
Yeah.
Well, when you got people partying at Daytona Beach thinking they're invincible, doing stuff like that, it's a matter of time before those sorts of things happen. What's up, Marlo? You're muted. How you doing?
Hey, Spencer, how's it going?
Yeah, it's going well. I'm doing well. You guys, I saw that other people were continuing to have open classes and stuff these last couple of days. I'm like, no, I'm not going to do that to you guys. So we're not going to get through everything.
Thank you so much.
We're not going to get through everything that's on the syllabus. We're just going to get through everything we possibly can.
Yeah.
But I've been thinking a lot about ways to assess you guys, and I'm curious, and maybe we'll do this through chat because then everyone doesn't have to talk all at the same time, hopefully. It looks like there's only 26 of you guys here, so you're not all, the whole class isn't really here. But I'm curious if I posted an exam on the titanium and opened it up right at the normal class time, would you guys be able to print it, do it, send a picture back to me? Because I don't know, I mean, you can just type in the chat and you can just type to me if you don't want to type to everyone, because I got to make sure everyone's got accessibility, right? Because some of you, I went on Amazon and I got this little electronic pen, so now I can write on stuff. So you can do it electronically, you can do it a hard copy, but it would be best if you could I could post the exam. We just have a Zoom meeting, so you're just working on it with the camera there. So I mean, I trust you guys, right? But I'm watching my faculty figuring out ways to make sure students aren't cheating on their exams. I'm like, well, I mean, that is a thing. Hey, Cedar, how you doing? So I'm seeing a lot of yeses that people. Okay, so I see some that don't have.
I don't have a webcam for my computer, and I can't use my phone webcam because I don't have a laptop or anything. So
Gotcha.
I would have to stay on the call, but I would not be able to show my face.
Okay, no worries. I mean,
you could always. There's a PDF app that you could use to take a picture of your work and then just email it to you.
Right, and you can also edit a PDF. So if you took a picture of it, I mean, I've been trying to find ways to make this work for everybody, and I got to make sure that it's accessible. How you doing, Jorge? I see you there. Unmute, Jorge.
I mean, what you can do is you can just download the PDF onto your computer and then use Word to just layer words over it. So if you don't want to print it out.
And that's what I was thinking for people who didn't have access to a printer, but I really want to be mindful of the technology that you have and not make it so somebody who's got all this technology is ahead of someone who doesn't and make it complicated, right? Because we still have to find a way for you guys to get some kind of assessment work back to me. And it looks like you're all isolated. So, I mean, I get it. My faculty are worried. Oh, they're going to look on their phone. They're going to look on the internet, whatever. I'm just going to trust that if you say you didn't do any of these things, you didn't do any of these things, and you're just going to do the exam. But I'm just trying to see how many people You don't have access. What's up, Chris? You in the islands there, dude? Looking good. Hey, Chris, you're muted. What's going on?
I'm sick. What's that?
What's going on? How you doing?
Doing all right. I'm doing all right.
Where's Sammy? Sammy. I'm trying to unmute Sammy.
Hello, how are
Hey,
you?
how you doing?
I'm doing fine.
That was pretty close.
Professor, with the exam,
Hold
would
on.
it be
Hold
like
on.
a
Wait one
timed-
second. I gotta mute everybody because I'm hearing somebody. All right. Here's how it's gonna be. So if you guys all go to participants and you open up the participants box. So if you go down, let me share my screen. All right. So I'm gonna share my screen here. So if you go down to the bottom, now it's not letting me show the Zoom screen. Well, anyways, if you were down here at the bottom of the screen, there should be a participants box. If you click on it, you'll get something that looks like this. And then next to your name or down here, there should be a raise hand button. Oh my gosh, now it's not even showing up. More. Probably on yours it'll show it. So let me stop the sharing of my screen. Manage participants. Nope, you know where it is? It might be under chat. Yeah, it might be under chat. I've been having so many Zoom meetings. I don't know. There's got to be a link. There's somewhere where it says you can raise your hand, and now I can't even see it. But I'm trying. There it is. Chris found it. All right.
Yeah.
So Chris,
Yeah,
how
it's
do you
under
raise your
participant.
hand?
Yeah, you just click on participants and then it says raise hand and then
Right. Okay. And then if I show participants, manage participants, then it shows everybody that's got their hands raised. So I see Sarah's got her hand raised, Chris does, Perla, Nick, Joan, Atria. Okay, a bunch of you got your hands raised. Good. You know how to do it. So you can put your hands down. That's cool. And I'll keep that window open on the side so that you guys can raise your hand. Because if everybody's talking at the same time, it's going to get really loud, and that will be complicated. So hopefully we'll be able to get through this. I guess hopefully your instructors are all bearing with you and trying to show you some degree of kindness, because there's a lot going on here, and I'm seeing that also with my instructors and students who are going on. So I see some hands that remain up. Sarah, did you have a question still?
Yeah, when would the test be?
Well, that's a good question. So we officially, if you look at the syllabus, we have today and then spring break, right? If I'm not mistaken, next week is spring break. And so we have had like a week off, which makes sense that we would postpone everything by at least a week. So, I mean, there was supposed to be a quiz today. That's clearly not happening. And so I would say probably we'll have a quiz maybe the Thursday after spring break. So we'll be able to talk today. You'll have spring break to work on the stuff we've talked about today. And I'm not gonna expect you to go ahead and do stuff without me talking about it. So again, how much are we gonna get through? I don't know. We'll get through everything. I'll try to keep you guys as up to date with those things as possible. And we'll try the quiz next week. There's options to take quizzes online, but it's complicated because then you
quiz next week.
Well, there was officially supposed to be a quiz today. Next week is spring break, so you off all next week. You don't have to worry about anything for this class next week. And then the following week, we would come back again and we'd have a quiz on the Thursday of that week. So does that sound right to you guys? Okay. Chris, you had a question? Your hand.
No questions here. I was just, so wait, the hand raising was just for answering questions, or what was it for?
Whatever. Anytime you want to participate so that I recognize that you want to interject, and I'll stop talking.
Oh, okay. We'll do.
All right. Andrew Lehman, did you have your hand up?
Yeah, so for the exam, it'll
Hold
be
on.
like,
1 second.
all right.
All right, you're good.
So for the, like how you're saying the exam, so we had printed out and we'd still take it during the class time, and then when
Yeah, I
class
think
is,
so.
like,
I'd
done,
like
we submit it.
Yeah, I'd like to keep this as real time as possible so that I'm not forcing you guys to do something out of the ordinary class time. That doesn't seem legitimate to me to make you guys, because you have other classes and everything's scheduled when it was scheduled. And that's something I have to be careful too with my teachers. They're like, well, I'm just going to do a Zoom meeting, whatever. I'm like, no, you can't do that. They have other classes that they have to go to. So what we'll probably do is I will get everything ready and I'll post it like 5 minutes before class starts, or maybe 10 minutes or whatever, give you enough time to get it downloaded or printed or whatever. And then I'll host a Zoom meeting. If you can join, great, because that way you can ask questions about the exam in real time. And then when you're done, you can just take a picture of it and send it to me.
Okay.
Then I'll grade it electronically and return it to you guys. That seems like the best plan as far as I can tell. I mean, you guys can always message me separately and say, hey, Dr. Hartmann, that's stupid. Let's try this or whatever. Perla, you had a question?
Yeah, I was wondering, what would the quiz exactly cover?
What would the quiz cover? Well, probably everything up into what we cover today. All right, so it'll probably be on gases and stoichiometry, balancing equations and doing some math with balanced equations. Okay?
Thank you.
All righty. Any other questions? 37 participants. That's pretty good. Pretty good. Wait, Atria, did you have a question?
Yeah. So when do you think the exam is? The quiz is the Thursday after spring break, and then the exam is.
Would probably be a week after that, I'm guessing. I don't have the schedule in front of me. So imagine everything being off by a week.
Okay. Thank you.
Sounds good. All right. I don't see any other questions. All right. So what I'm going to do is I am going to share my screen and share my screen. I'm going to move this and go to, okay. So here we are in week 9, in case you were wondering what's going on. Actually, let me go back to the class. Week 9. All right, so week 9. So we've been talking about balancing equations, and let me ask you guys if you have any questions, and I'll go back to the chat box. Does anybody have any questions about balancing equations? Anything you want me to go through on what it means, how to do it? All right, I don't see any questions about balance. They're pretty straightforward. Just keep in mind that there's a couple kinds of problems you might run into. I would just give you a word problem, and then you'd have to convert it to equations and then balance it. So that's a complicated question where I might write something out, and then that tests your naming and your ability to write equations. Or I could just give you an expression with symbols and ask you to balance it. And we're also going to talk about types of reactions today. And so those are relatively predictable. So I might say, okay, this is a combustion equation. And combustion is always something plus oxygen typically produces carbon dioxide and water. So they're relatively straightforward kinds of things like that. All right, so let's just go through this PowerPoint. There's going to be some interesting stuff in there, but all right, so types of chemical equations. I'm going to try to keep this handy so I can see if anybody has any questions. And if I don't see your hand, just chime in. You might be muted. I think a lot of you are muted, so even if you talk, I'm not going to hear it, and that's fine. But if at any point you have a question, unmute yourself and chime in. That'll probably be the best way to get through this. So these first couple slides are just about balancing equations, so I'm just going to go through those pretty quickly because I don't think we want to worry about those. We did that, right? A balance. All right, so types of chemical reactions. So there's basically 4 kinds of reactions that you're going to want to be able to recognize. So I'm guessing you can all see this: composition, decomposition, single replacement, ionic/double replacement. There's actually one more in there, acid-base neutralization, and that might very well be on the next slide. Nope, they didn't do it. Okay. So if you look at the symbology, they're pretty basic, right? A composition equation would be where you take 2 simple things like elements and make a new compound. So for instance, you might take sodium and chlorine to make sodium chloride. And then a decomposition reaction would be the opposite. So I'm full of technological wonders today. So I'm going to see if I can't stop this share, and I'll go to my iPad and I'll try to give you some exact examples of this guy. So share screen, iPad, iPhone via cable. Come on, baby. Yes, look at that. Wow, this is like totally amazing.
That just happened.
That just happened. All right, so
Oh, baby.
now I got to figure out how to work this thing. So all right, here we go. Touch this little thing down here. Oh my gosh, come on, baby, don't fail me now. Oh, gotta turn the pen on. I'm learning, people. I am totally learning. Eraser. All right, you can see that I was working on this. All right. Okay, so if we were going to do a composition reaction between sodium and chlorine, how would I write elemental sodium? Well, I'd write it as Na. Let me get this thing out of my screen so that's not there, right? Plus chlorine. Anyone want to tell me how I'm going to write chlorine as an element?
Cl.
Close. Cl is one of those guys. Remember chlorine? Cl2, yep. And typically you're going to want to put states in those. So sodium is a solid, Cl2 would be a gas. And then we want to complete that reaction. So this is where a whole bunch of things that you've been learning comes into play, right? So if I just gave you this on a quiz and said, complete this reaction, you'd have a couple things to think about. You'd be like, well, crap, I don't know what's going on there. And you'd recognize, wait a minute, this looks like a composition where I'm taking A plus B goes to AB. In this case, A is sodium and B is chlorine. What's the combination of A and B? In this case, it's probably easiest to write the name of what you're going to form. So what do you get when you combine sodium and chlorine?
Sodium chloride.
Absolutely. So I know that I'm going to produce sodium chloride. Then the question becomes, what's the formula for sodium chloride? Well, then you got to go back to remember all the stuff you learned about naming. Sodium's in group 1, so it always forms what kind of ion? Group 1, anyone? Bueller, plus 1, that's what I thought you said. Chlorine, remember our buddy chlorine, it's in group 7, so it's going to form a -1. So you know the formula for sodium chloride is NaCl, right? So that would be your equation that you would write. So let me change colors here. Let me go to black. So you would write Na solid plus Cl2 gas produces NaCl. Hopefully you all know that sodium chloride is a solid. All right, now we look at that. So we've completed our equation. Is that balanced? Is that chemical equation balanced? Nope, I see a bunch of no's. And so that would be the next thing that you'd want to do. So you can kind of see how all this stuff is building, right? First, you had to learn how to name. Then you got to learn how to put things together. Then you got to write balanced equations or complete an equation. Then you got to balance it. And after that, we're going to do math, right? If you have 3 grams of this, how much of this can you make? It gets deeper every time we dig into it, all right? So how do you balance an expression like this? Well, typically, remember we said you want to balance it with something that only appears in one thing. Well, in this case, sodium and chlorine both appear over here. There's one really simple way to balance it involving a fraction. You could put a half here, right? That's totally legitimate. If you want to balance it that way, you've got one sodium here. Why is my pen not working? Turned it off. You got one sodium here and one sodium here. You've got a half times Cl2. Oops, sorry about that. And a half. Sorry about that. I'm not being. You got a half times Cl2, so that's 1 Cl. You got 1 Cl. So that's actually balanced, but it's not pretty. Nobody does it that way. Well, actually, we're not going to do it that way. So what would be the real way to balance this expression? You would say, well, let me get rid of this half. I know that I have 2 chlorines over here and I only have 1 chlorine over there. So I know I have to put a 2 in front of that to balance the chlorines. So now I've got 2 chlorines here, 2 chlorines here, but now I also have 2 sodiums, so I have to put a 2 in front of that to balance it. So now this expression is balanced, right, and completed. So that's the kind of thing you should be thinking about when you're going through homework and problems on these things, right? So recognize types of reactions. So this is a composition or a synthesis reaction. A plus B goes to AB. And typically, these are almost always going to be elements. There's some exceptions, but I'm not going to give them to you. So in this case, you should be able to recognize it because you'll have elements over on this side. So sodium and chlorine, or maybe calcium and bromine, right? Any of those 2 sorts of things to form a compound over here on the right. Okay. Here's an interesting question, you tech savvy people out there. I probably can save this, can't I? I could save this so you guys could have it, but I've never done that before. Let me see. Drive. Look at that. I'm going to save it to the drive. Upload. All right, cool. That's done. So that's saved. So now I'm going to trash this because I don't care. And get rid of the, okay. All right, so let's look at the second kind of reaction. The second kind of reaction was a decomposition reaction. All right, why am I not writing? And a decomposition reaction is just the opposite of a composition reaction. So you start with one substance and you break it down into the pieces that make it up. And these can be more complicated, but again, I'm going to try to stick to simpler ones. So in the previous example, we had A, B. A and B were both elements, right? So an example might be something like HGO. So this is mercury oxide. In this case, it's mercury 2 oxide. And it's going to go, well, what are the 2 elements that are in mercury oxide? Easy question for someone to jump in here. Anyone? What are the 2 elements that are in mercury oxide?
Mercury and oxygen.
There you go. It goes to mercury, Hg, and O, right? So mercury as an element is written just as Hg. Remember, that's one of the few that's a liquid at standard conditions. What about O? If I have oxygen as an element, do I write it as O?
No.
I have to write it as O2, right? So now I'd have to go back and balance that expression. I know I have 2 oxygens here and only 1, so I'd have to put a 2 there and a 2 there. So it's pretty straightforward in terms of recognizing how to complete and balance a decomposition reaction. They're really not that complicated. Okay. The ones after that get to be more complicated. These things called single replacement reaction. All right, the name kind of applies what's happening, single and replacement. So if you think about it, something's getting replaced by something else, right? Okay, so an example that they give you is something like this, A plus BC, and notice there's a little AQ next to BC, goes to AC plus B, all right? So A plus BC goes to AC plus B. In this case, these are not necessarily elements. So A, B, and C are not elements. They can be any sorts of things. So I want to give you some simple kinds of examples where that might be the case. All right. So an example of a single replacement reaction, we might have something like, how about, I'm trying to think of one where we could go with this. So let's go. And let's go with Eg. So in this particular case, you have one single thing. In this case, I picked silver. And here I have something called, oh, anyone want to take a stab at the name of that?
Lead.
Lead.
Oh,
NO3.
lead nitrate.
Yep, lead nitrate. And this is actually, lead has 2 oxidation states. You weren't on the hook for memorizing these. Lead can be +2 or lead can be +4. This is actually lead 2 nitrate because of that 2 there. And in a single replacement reaction, so let me erase this stuff here. If you were just going to follow the rules that we wrote here, A plus BC goes to AC plus B. Anyone want to take a stab at what the AC looks like? What 2 things are going to trade places?
Nitrate.
Oh,
well, the nitrate's moving from silver to...
Okay, that's one way to do it. Absolutely, there's nothing wrong with that. One way to look at it is to say that this, why is that not liking me? Help me out here. I didn't turn it off. All right, let's pick that one. This is going over there, right? That's one way to look at it. But I prefer, if you think about it, it's called a single replacement reaction, right? So really, this guy is replacing this guy, right? So that's a better way to think about these kinds of reactions. Something is replacing something else. So in this particular case, silver is replacing lead, right? Single replacement. Why wouldn't silver replace nitrate? Well, let's think about that for a couple of reasons. Silver and lead are both metals, right? Silver forms a plus compound, lead forms a plus compound. Nitrate is a negatively charged ion. Is something that's positive going to replace something that's negative? Probably not, right? It's going to replace something that it's like. So you could also, next to the name, put like replaces like, right? So a metal replaces a metal, right? If I had a non-metal over here, an anion, it might replace the anion, right? But typically you write them this way, right? So in this case, if silver replaces lead, right? And the same as the first couple of ones, instead of trying to write the formula first, it's so much easier just to write the name. So if I combine silver and nitrate together, what compound do I get? Well, that's easy. I get silver nitrate. That doesn't look like silver nitrate. Let me rewrite that. When I combine silver and nitrate together, I get silver nitrate. What's the formula for silver nitrate? Well, silver is +1, nitrate is -1, so the formula would be AgNO3, right? That's going to bother some of you. Why? Because the nitrate has a 2 over here, and there's only 1 nitrate over here. But that's because of what it's combined with. Over here, silver's combined, nitrate's combined with lead. Lead is +2, so there has to be 2 nitrates to balance the lead. Silver is +1, so there only needs to be 1 nitrate to balance the silver. The way you fix that is when you actually balance the equation, right? So let's get rid of this, and let's just try this again. So I'm going to rewrite it. Okay, I'm going to rewrite it. All right, people, help me out here. What am I doing wrong? Is that problem? All right, now, I'm not sure why I didn't like that thin pencil, but all right. I'm sorry, guys. I don't know why I'm doing wrong here. Ag plus Pb NO3 2 produces Ag NO3 plus Pb. The lead just comes out by itself. That looks awful. I'm sorry, but I'm trying. This looks like Hg. Oh, I see what the problem is. I'm way off the top of the screen. All right. So now we just have to balance it. So over here I have 2 nitrates. The only way to have 2 nitrates on the right is to put a 2 in front of that guy. And by putting a 2 in front of that guy, that also means I have to have 2 silvers. So in order to check that, let's just go back and count. 2 silvers, 2 silvers, so that's good. 1 lead, 1 lead, that's good. 2 nitrates. This 2 is in front of the whole thing, so there's 2 nitrates, so that's good. So I've balanced the equation by doing it that way. So writing equations takes a lot of practice. It's like writing names. Unfortunately, there's no easy way to get out of it. And the next one was double replacement. And this should make sense in and of itself right away, the double replacement reaction. So that's going to look something like AB plus CD goes to AD plus CB, where you're trading places. But always what happens is that the ones that are the same trade places. So you could imagine that the first part, all right, by the way, these compounds that have 2 parts are always ionic, right? So this is an ionic substance. This is ionic. This is ionic. So that's kind of a clue to yourself as well. When you're looking at these guys, you can say, oh, I know that's going to be a double replacement or a single because they're ionic type substances, and I can just switch them over. The other thing I failed to put in here is that little AQ, right? These reactions always happen in solution. And we'll talk about solubility. Kay, you had asked me about solubility, and this is where it comes up again. We're going to talk about some solubility guidelines today and what's soluble and what's not soluble. Well, let's pick a little bit more complicated example. So let's think about one that we can write here. So we'll pick lead again, even though you didn't have a whole lot to do with lead. So let's go with PbNO3 2 plus K2S. All right. Aqueous. This is aqueous. At this point, I don't expect you to know those are soluble. We'll talk more later on today in terms of how you know something is soluble and how this reaction can happen, right? But these guys have to be able to be soluble in order for them to change places. And even though I'm just introducing this type of reaction now, it'll become more clear when we talk about what happens when you put something that's ionic in solution, all right? But if we are just following the guidelines, even if we don't have any idea what we're doing here, because oftentimes that's the way I've learned things, I don't know what I'm doing, but I certainly can follow rules. So the rules say A, B, C, D, A and C have to trade places. So I can see that this is A and this is C, right? I'm not worried about the fact that that's a 2 and there's a 1 by the lead. I just know that they have to trade places. So I know that these guys are trading places to form 2 new things. I don't have enough room over there to write those 2 new things, so I'm going to write the 2 lines over here, all right? And again, we've been trying to do this via name so far, all right? So right now, this is lead 2 nitrate. And the new one, the lead is not going to be the nitrate anymore. It's going to be with this guy, right? So what do you call that when lead gets together with sulfur? Anyone want to take a stab at that?
Lead sulfide.
Exactly. This would be lead sulfide, and we just got to put one more thing in there. It's lead 2 sulfide. And what's the other product going to be when the potassium goes over here?
Potassium nitrate.
Yep, potassium nitrate. So when you're doing reactions like this, the easiest thing to do, what I found by far, is to name them out first rather than trying to force yourself to write the formulas. Because what you're going to try to do, and I've seen it all the time, is you're going to be like, okay, this K2 is going to come over here and this PB is going to go over there. So I'm going to get K2, NO3, 2, and PBS. You might get them right, you might not get them right. In this case, that one happens to be right. This one, we wouldn't have those 2's in there, but I don't want to leave that there because that's not how I would recommend you do that. I always recommend that you write the names of what you get when you switch these partners, right? And then go from there. So once I know that that's the name that I wanted to have, Then I'm going to go ahead and try and write the name. So I know lead 2 is Pb plus 2. Oop, I didn't want green. Sorry about that. I wanted to go to black. That's not too sharp. Black. Pb plus 2. Sulfide is S minus 2. So if you remember your formula writing, just crisscross. And so you should end up with Pb2S2, which is really PbS. So lead sulfide is one of the products. And that may be what you predicted. If you just swap those guys, you get lucky on that one. Yeah, you know, sometimes you get lucky. And then the potassium nitrate, well, again, I remember the symbol for potassium is K. I know it's in group 1, so it forms a +1 ion. I memorized that I assimilated that the nitrate is NO3 minus 1. Same story, crisscross. So I end up with KNO3. So I'm down with that. I've got my products, my starting materials. Now I'd be asked to write the whole balanced equation. So let me just go up here and see if we can't write this whole thing. Wow, that's taking forever. Come on, babe. Come on, come on, come on. All right. So we'd want to write the whole thing. So I would start with Pb NO3 2. These are aqueous plus K2S aqueous produces, and I don't have a whole lot of room, so I'm just going to write down here, PbS plus KNO3, right? Whether these are aqueous or not, you don't know yet. We haven't learned the solubility guidelines. But I'll tell you right now, nitrates are always soluble. So I'm going to put a little AQ next to it. Anytime you have a nitrate, it's soluble, right? Nitrates are always soluble. This guy, not so much, okay? We'd have to balance this particular equation. And so I'm going to do what I did before. I'm going to look at the elements and see if they're even. So I've got one lead here and one lead there. So lead is okay. I've got 2 nitrates here, but I only have 1 nitrate there. So I know that I have to fix that. So I'm going to come over here and I'm going to say, okay, if there's 2 nitrates there, I have to put a 2 in front of this to make the nitrates happy. All right. Going back to checking my elements, there's 2 potassiums there. Oh, now the potassiums are happy because I put that 2 in front of it. He's okay. And I got 1 sulfur there and 1 sulfur there. So sulfur's happy. So I wrote the expression, I completed it, I balanced it, everybody's happy. All right. So those are the 4 kinds of reactions that typically you'd run into. All right. So there's a composition, decomposition, single replacement, double replacement. The kinds of things you can expect to be asked to do would be recognize it. What kind of reaction is this? So I'd give you a reaction and say, okay, of the 4 types, what is this? Single replacement, double replacement. So that's an easy, super easy question. All you got to do is recognize it. The more complicated one is to complete it. The most complicated one is to complete it and balance it, right? And then we're going to move on to talk about, why does this reaction happen? In the real world, the only reason these guys want to trade places is if they can go to something that's more stable, right? And more stable means not in solution. So in real life, this guy is a precipitate. Lead sulfide is insoluble. So when you mix a solution of lead nitrate, which is aqueous, and a solution of potassium sulfide, so you'd have two beakers with clear solutions in them, you mix them together, you get a precipitate of black lead sulfide. That's what drives this reaction to happen, the formation of something that's not soluble, right? And then this guy just hangs around for the ride and watches that reaction happen. And we're going to see a lot of those kinds of reactions, right? Then you could also ask yourself, what would I do with that? Well, I might say, if you've got 5 grams of this and 5 grams of this, how many of each of these do you make? So then it's a matter of, I got to change to moles. And I got to use the balanced equation to convert things from moles of this to moles of this. And then I got to go from moles back to grams. And that's about as complicated as it gets. But honestly, that's a lot. All right, I'm going to stop there for a second and see if anybody has any questions. Anyone have any questions? Anyone? Sarah Williams raised hand. Sarah, do you have a hand up?
Yeah. I couldn't tell what you wrote for when you were writing the single replacement. Was it 2AG plus P, and then was there a 4 after NO3?
Nope, there wasn't. It was 2AG plus PbNO3 parentheses 2 goes to PB plus 2AgNO3.
Oh, okay.
So everything balanced out. That makes sense?
Yeah.
Okay, let me see if I can find that list again of participants. Anyone else have a question? I'm trying to find my list here. Cedar, is that a question? No?
Professor?
Yeah.
So on a test, you would give us just the reactants, and then we'd have to figure out the rest?
That would be a harder level question. So I probably would do that again. So I would give you one, like, let's say I gave you this particular expression here, right? I would probably give you this part here and say, complete and balance this reaction.
Okay. So
what you'd be so what I'd be testing is a number of things. I'd test your ability to recognize this as a double replacement reaction, and then your ability to complete it correctly, and then balance it. And so, as is always the case, I'm going to give you as much partial credit as I can, right? And so I will be looking at those particular things, but I mean, you have lots of practice in the homework in completing equations and balancing them and doing those sorts of things. And honestly, of the things you're going to learn in this class that will help you in the next chemistry life, probably not so much the completing of equations, but I think the balancing of equations is really, really crucial. Marlo, I think you had a hand up.
Thank you.
Yep. Marlo, did you have your hand up?
Yeah, quick question. From the would you happen to have the solutions to the packet that you gave us the last day that we were there? The one with the
I probably
gases.
do. I honestly don't remember what I gave you on the last day. So if you just send me an email and remind me of which things I gave you, I'll do my best to get those solutions posted.
Okay, sounds good. Thank you.
All right. Any other questions? I'm trying to see hands up here and I'm not seeing any. All right. Stop that. Stop this. All right. Look at that. You guys are falling asleep out there? You're more comfy than in class, huh? So let me ask you a question. If you had a choice of in-person or doing Zoom classes, which would you rather do?
In class.
In person.
In person.
In person.
That's what I thought.
Definitely in person.
That's up for debate with me.
It's more fun. You can't see me dancing and doing other fun stuff on my couch. Plus, I'm sitting, which I hate doing. I'd much rather. I actually brought a whiteboard home and tried to write on it, and it was so awful. You couldn't see it with my computer. I'm like, oh man, I got to find a better technology to do this. So,
have you you're using an iPad, right?
Yeah. Well, yes, I am.
If you download an app called Notability,
yeah,
it's pretty useful when it comes to this.
Notability.
It's an app that my research professors use, and it works. It's almost like a whiteboard. It's perfect.
Okay, so it's better than writing on notes like I've been doing?
Yes, 100% better.
All right, that's good to know. Notability, huh?
Yes.
Can you send me an email or something just to remind me about that?
There's also another app called Good Notes. That one works also good.
Okay. Okay, I see that. Yeah.
Professor.
Yep.
Are you using the Apple Pen?
Am I? You know what? No, I bought a cheap pen on Amazon. Well, not cheap. It was $32. But the iPads I brought home from work, I brought one home and it had an Apple Pen, but it hadn't been charged for a while, and it was totally dead and it wouldn't take a charge. So I'm like, I need something quick. I just got this, and it seems to work pretty well. I'm actually, the problem is that if I put my hand on the iPad, my pinky will write on the iPad as well. So it's not super high tech, but
you could disable it, I think, because mine disabled Palm Touch.
Oh, did it? Well, I'll have to check. I mean, I honestly don't know. I don't even know which one I bought. One of my faculty said, "Here, try getting this." It was super cheap, and it came the next day from Amazon Prime. So I thought, I'm going to give this a shot. I'm like borderline at the edge of my ability to process new technology, in case you guys couldn't tell. It's a little complicated, but I have to laugh because I got faculty who like, they don't do anything at all with computers. And so they're learning to do Zoom and figuring out how to get stuff to students. And I'd like, this might go on through summer, and some of you have summer classes. Are you going to be okay doing this in the summer? And a few of them are like, I'm never doing this again. Other ones are like, yeah, I could do this. But it's taken them a lot of time from going in person to online. They say they're spending 10, 12 hours a day on the computer all day interacting with students. So kudos to them. But yeah. All right. So let's go back to where we were with the PowerPoint. So composition reaction, we mentioned this. You just take the compounds from the elements. I just want to get back here and make sure I can still see the chat. Sorry about that. Move this over here. And again, keep in mind the state symbols that you might run into, and also just the names, right? So if I say nitrogen plus hydrogen, of course, ammonia is a common name. You wouldn't recognize that. Anyone want to take a stab at what the real name for this compound would be? NH3? Anyone? It's a binary covalent compound. So you name this and then this plus IDE. Anyone want to take a stab at that? Nitrogen trihydride. Oh, yeah. Okay. And then composition reaction. You can also form compounds from simpler substances like this one, but I'm going to try to stay away from that because predicting what you get over here is really, really beyond the scope of this class. So I put it in here so you can see that you can make more complicated things from simple things. All right. So in this particular case,
Professor?
Yes.
We can't see your screen.
Oh, you know what? I got to share my screen. Why? Thank you for chiming in there. That was, I apologize. All right. My wife yelled from the back, doofus. All righty then. All right, there's my screen. Let me bring this back up. Sorry, guys. All right. Where is it? Oh, well, I'm not going to worry about that. All right. So where'd I go with the PowerPoint? There it is. Okay. Sorry about that. So a composition reaction. So when you have some simple things, you can go to more complicated things from elements. These are the only kind I would ever ask you to complete. Okay. And even then, it's going to be complicated in terms of completion because you may not know how they go. Remember, we were talking about covalent compounds. Predicting what you get isn't obvious. So I would have to give you like the name. So I might say nitrogen plus oxygen produces dinitrogen tetroxide. Okay, something like that. And if I gave you something like this second one, I wouldn't ask you to complete it. I might ask you to I might ask you to balance it. I might also ask you to identify it as a composition, right? So if you're looking at this, you're taking two things, which looks like A, B, and going to A, B, one more complicated thing. So composition reactions don't just have to be elements. They can also be compounds going to more complicated things. And the same, of course, is going to be true for decomposition reactions. So combustion reactions is another kind, and we've talked briefly about combustion reaction. And essentially, it's the reaction of a simple substance with oxygen. These guys here are more complicated. These are the kinds that I'm going to ask you about right here, where you have something that has carbon and hydrogen, you're adding oxygen, and you're always making carbon dioxide and water. So this one down here at the bottom is the standard kind of combustion reaction, right? And that's the only one I want you to be aware of. Although you might look at this and say, wait, isn't iron plus oxygen, isn't that combustion? Am I not reacting iron with oxygen? Yes, it is, but it could also be called an oxidation reaction. So it has a whole bunch of different names. right? And again, my goal is not to confuse you. My goal is to try to make this as simple as possible and get you ready for the next chemistry class where they're just going to assume you know these things. They'll be lecturing and they'll say, okay, in this double replacement reaction or in this combustion reaction, and then I will feel comfortable knowing that you've at least seen it. So it won't be like, what the heck is that? Where'd that come from? All right. We balanced the combustion reaction last time. So it's just a matter of practice, but the key is to always balance oxygen last. So we're not going to worry about this. And for now, oxidation reduction, I'm going to throw it out there, but you're not going to be responsible for balancing these because there's just way, way, way too much subtlety in a redox reaction. But if you look at them, what you'll notice is that some things are losing electrons and some things are gaining electrons. That's why we call it an oxidation reduction reaction. So for instance, here, iron starts out as a free metal. Its oxidation number is 0. Chlorine is a free gas, starts out at 0. But when you make the compound, iron becomes +2 and chlorine becomes -1. So they've traded some electrons, hence oxidation reduction. Decomposition, right? So we mentioned this, and here's an example, mercuric oxide or mercury 2 oxide. And it's going to the element and oxygen. So this is a pretty much straightforward kind of example, but there are certainly more complicated examples that you can have where big things decompose into small things. This is another kind of classic example, a carbonate. So if you heat a carbonate, it typically liberates carbon dioxide and you get the metal oxide left over. And probably the most common example you're ever going to see of this is baking soda. So you might take hydrogen carbonate. I'm just going to turn my phone down. And heat it up and it makes carbon dioxide and water. And that's this is the kind of reaction similar to this that might cause not a yeast bread, but like a quick bread. If you're making banana bread or something and you put some baking soda in it or baking powder, this is the kind of reaction where this carbon dioxide is what causes that bread to rise. All right, so I believe we are at the, nope, we don't want to watch that. Single replacement. So in this particular case, you've got a free element that replaces another element in that compound. So we've talked about a couple of these, and you can look at what's happening. The zinc is replacing the copper, right? These guys are both metals. So the zinc is never going to replace the bromine, because if it did, you would end up with a compound of copper and zinc, which doesn't exist. Metal, I don't want to say metals don't make compounds with each other. They make alloys, but as far as you're concerned, they're not going to form a compound. So it's always going to replace the same thing. So zinc would replace copper, right? Or if you look at the second example, chlorine is replacing bromine, right? So chlorine and bromine are both nonmetals. The chlorine in this case would replace the bromine. Up here, the zinc is replacing the copper, right? So this is your A, and this is the B, it's replacing that guy, and this is your A, and this is the B, and it's replacing that guy. They're relatively straightforward. I don't mean that they're never going to give you questions or you're never going to have problems trying to figure them out, but they're generally pretty straightforward, right? Same thing is true. Let me go back a slide. So single replacement reactions, couple things to note that they're often what we call oxidation reduction reactions because the zinc here doesn't have a charge. It's just zinc metal. It doesn't have a charge on it. But when it's in the compound, now it's all of a sudden it's zinc 2+. The same is true with chlorine here. Chlorine as a free element doesn't have a charge, but here it's Cl-1. So something happened to it where it gained a charge. The other thing to keep in mind is that this is an ionic compound. I've got a metal and a nonmetal. This is ionic. I've got a metal and a nonmetal. So single replacement reactions often involve at least one ionic thing and one thing that's not part of a compound. And then if you go to double replacement, they're always ionic. So KCl, potassium chloride, that's an ionic substance. Sodium nitrate, that's an ionic substance. And the products are both ionic substances, potassium nitrate and sodium chloride, right? They only happen in solution. That's important to know. So if you had solid potassium chloride and solid sodium nitrate, and you shook them up together, nothing would happen. right? They only happen in solution, and we'll get to that a little bit later. But what happens in solution is that these ions separate. They move apart in solution, and then they can start to dance and trade places with each other. Another example of a ionic or double replacement reaction is the neutralization of an acid and a base to make a salt in water. And I believe we talked a little bit about that when we were naming those compounds. So for instance, here's an example. If you've got hydrochloric acid and sodium hydroxide, the H and the NH are trading places, right? So now the H goes together with the OH, and we can write that as H2O. That's the same thing. HOH is H2O, and the Na gets together with the Cl form NaCl. So we say that when you mix an acid and a base, you get some salt. In this case, it is sodium chloride and water, right? And then when you're done, you just have a neutral solution. There's no acid or no base, right? And that's kind of the example of why you would take an antacid. So if you take a Tums tablet, you're taking aluminum hydroxide, and it's reacting with the hydrochloric acid that's in your stomach to make aluminum chloride and water. Neither of these are acid or base, and it neutralizes the acid that's in your stomach. Okay, so we've taken some time to do this. Let's go and look at one of the resources for this week. And I've been talking a lot. I know none of you are in groups, so you can't work together, but maybe you can take a little bit of time and try to do one of these practice things on your own. So let's look at, I think it's this one. Nope, that's not the one I wanted. Sorry. This one might be the one that asks you to complete them. Well, that's awesome. I have no idea why that's in Greek. I don't know what happened there. Somehow the font got changed. Maybe it's in the next chapter. Let me go back. I might have them in the next resources and activities. Let me go back to here. So much more fun in person. All right. Might have to dig around and find it. I don't know where it went.
Professor, there is a way to split us up into groups to do group work.
Oh yeah, I see that.
Yeah, I posted it in the chat. There's a breakout rooms button, I guess, since you're the host.
Yeah, but I'd have to put you in groups, or maybe you guys could self-select in the groups. I'm just wondering if, and I'm happy to do that. I'm just wondering how we would, I see that, yeah, groups. I just want to, here it is. Why is that not coming up? Trying to find the one that was the one on.
I think the host chooses the group.
Yeah, I see that. It's got to be. I'm trying to remember which one was the one that was easy for you guys to work in groups. Maybe it's this one. There's so many things on here. This is one of the ways to do it. This is more simple than I wanted. I was trying to find the slightly more complicated one. You know what? It might not be there. It might not be time to break up in groups yet. Tell you what, I'll talk for a little while yet, and then we can go from there. The more complicated ones are in the next chapter. All right, so bear with me for a moment here. And let's actually just move on to this one. All right, so I don't care about the mole highway. All right, so here's what I want to think about. And this is the kind of stuff that we're going to have to kind of get our heads around, because honestly, I'll be frank with you guys, recognizing types of equations, you know, this is a single replacement, this is a double replacement, is really low in the scheme of important things for the next chemistry class you're going to take. The stuff that we're going to talk about now, using a balanced equation to do chemical calculations, is probably the single most important thing you're going to get out of this class, right? So we'll spend quite a bit of time on this. And that anecdote I told you a long time ago, when in doubt, convert to moles, that's really going to hold true here, because when we use balanced equations to calculate going from a starting material to a product, we have to use the balanced equation. But if you remember, when you have a balanced equation, these numbers, like this 2 in front of this zinc sulfide, that 2 means a bunch of things. It means I have 2 molecules of zinc sulfide, or 2 formula units of zinc sulfide. But it also means I have 2 moles of zinc sulfide. What it doesn't mean is I have 2 grams of zinc sulfide, right? The problem is that when we do things in the lab, we measure things. We measure grams, we measure liters, we measure pressure. We never measure moles when we're in the lab. But the only thing that lets me go between one substance and another is moles. And so it's really critical that we make the connection between how we do these particular problems, right? So for instance, without giving a whole lot of background, we could look at this particular problem. So if you take a mixture of zinc sulfide and oxygen gas, all right, just for fun, all right, what kind of reaction is this, all right? Anyone want to take a stab at that? What kind of reaction is this? Zinc sulfide plus oxygen goes to zinc oxide.
The single reactant?
Well, look at what we've got here. We've got an AB plus a C. Is this any of the ones we've looked at?
It's none of the ones we looked at.
It's not really any of the ones we looked at, right? That's not even fair. How can I throw that? What kind of reaction? If you had to take a stab, though, I mean, what does it look like is happening? It looks like it kind of looks like a replacement reaction, but really what's happening is that I'm taking this oxygen and I'm combining with both the zinc and the sulfur, right? It looks like I'm breaking this apart and adding some oxygen to the zinc, and I'm also adding some oxygen to the sulfur, right? Yeah, so I would never ask you to identify that particular reaction, but it doesn't mean we can't do any math, all right? So for starters, it's balanced, right? I've got 2 zinc over here. I've got 2 zinc over here. I've got 2 sulfurs over here. Hopefully you all see that. That 2 goes for this whole thing. So there's 2 sulfurs over here. 3 times 2, I've got 6 oxygen atoms over here. There's 2 in this one, and there are 2, 4 over here. So 2 oxygens and 4 oxygens is 6. So it's balanced. I've got the same number of each atom on both sides of the expression, right? So that's the first thing that's important, is that that expression is balanced, okay? But here's the kind of question that you might run into, right? It's saying, okay, how many grams of zinc oxide, which is this guy, how much of this can you make if you start with 1.6 grams of oxygen, all right? So I'm gonna, before I switch to my iPad, I'm gonna write this over on my iPad, and it probably would be useful for you guys if you wrote that down on a piece of paper or something, because we're gonna kind of go through this and see how we would solve a problem like this. Yeah, always something. It's probably not going to let me erase that. Oh well, whatever. So 2ZnS plus 3O2 goes to 2ZnO plus 2SO2. All right, I'm going to switch over to my iPad. Share screen. Same. All right. Thinking about it, thinking about it. All right, there it is. So I wrote down that formula, and it says we have 1.60 grams of this stuff, and it's asking us how much of this stuff can we make? All right. So this is a typical chemistry question. This is like when people think about chemistry, this is the kind of question they think about. I'm giving you some amount of this guy, and I want to know how much of this guy can you make, right? How much can you make? So here's some of the things, the questions that may or may not be rolling around in your brain, right? What about this guy, right? What about oxygen? You never said anything about oxygen, all right? Here's the typical answer I would give you. If I don't tell you anything about oxygen, you don't have to worry about oxygen. That's easy. What it means is that there's enough oxygen given that everything's going to happen as it should. What about the sulfur dioxide? You didn't ask me about sulfur dioxide. Well, I didn't ask you about it yet. I might at some point, right? So really, what I'm asking you is, if I give you this, can you convert this into that?
We were, it was 1.60 grams of O2, not zinc
Oh my
sulfide.
gosh, thank you. I can't even read my own question. If you were given, look at that, watch this. Look at all, I'm getting good at this. 1.60 grams of oxygen. The problem would have worked even the other way with that, but it won't match the numbers on your on the PowerPoint. So it's perfectly acceptable to do this. All right, let's go to green. If you were given 1.60 grams of oxygen, how much of this can you make? So I changed the question. What about this? Don't care. I know that's hurtful that I don't care about that guy, but I don't. Same with this. DC, don't care. They didn't ask you about that. You don't have to fret or worry about that. Are they needed? Yeah. Do you need zinc sulfide to make zinc oxide? Yeah. But it didn't ask you about zinc sulfide, so you really don't have to worry about that. All right. What's important that you recognize here is that you can write some ratios. I'm going to write a ratio for you and see if this makes sense to you. 3 moles of O2 equals 2 moles of zinc oxide. See where I got that from? The balanced equation. There's a 3 in front of this, and there's a 2 in front of that. And so I wrote this relationship. 3 moles of oxygen is equal to 2 moles of zinc oxide. Now, mathematically, is that really true? Anybody? Does 3 equal 2 in anybody's book?
No.
Nope. But what's true is that in the production of 2 moles of zinc oxide, I'm using 3 moles of oxygen. That's always true based on this balanced equation, right? So I can write that equality. I could also write this, 3 moles of O2 for every 2 moles of zinc oxide, right? And I would decide how to write this parentheses depending on what I started with. I want to put what I want on the bottom to get rid of it and what I want on the top to move forward, right? But this is the only relationship I can get between these two substances, right? The only relationship I can get is 3 moles to 2 moles. That's all I get. But I wasn't given moles. What was I given?
Grams.
I was given grams. So can I use this relationship? If I want to go from grams of oxygen to grams of zinc oxide, can I use this relationship as it's written?
No.
Not as it's written, right? Because the units don't work. So if I want to make use of this relationship, either this one or this one, what do I got to do to that?
Convert to moles.
Yep, absolutely. Remember my handy dandy slogan, when in doubt, convert to moles, right? So the question said, you know, how many grams of zinc oxide can be produced? So I look at this and I say, well, zinc oxide is a product. I want to make some of that. You're giving me oxygen, so it has to come from that. So I know I have to start with this. So I'm going to start with 1.60 grams of O2, right? I know over here I want to end up with grams of ZNO, zinc oxide. I know that's what I want to end up with. I can't do that in one step because these units aren't correct. But I do know from the periodic table a relationship between grams of O2 and moles of O2, right? From the periodic table, I'm going to give you the easy number, 1 mole of O2. What's the grams that goes with that? Anybody remember?
16.00.
Absolutely. You guys remembered your periodic table. That got in there. Nobody even looked at that. That must have been assimilated. I hate it when that happens. 16.00 grams of O2 is 1. Now I've got moles of oxygen. Now I can make use of this relation.
That doesn't work. That's only 1 oxygen. It needs to be 2, so it's 32.
Oh! 32 grams of O2, 1 mole of O2. Let me erase that so it looks pretty. Cedar, you're keeping me on my toes. 32 grams of O2 is 1 mole of O2. Balanced equation says, okay, now I wrote it with oxygen on the top and zinc oxide on the bottom. Did I have to write it that way?
Nope.
Nope, I could have written it however I want because it's equal. You can put whatever you want on the top or the bottom. So here you can write 3 moles of O2 for every 2 moles of ZNO. Uh-oh. I'm almost there. That doesn't quite get me to grams of zinc oxide. I'm headed in the right direction though. Moles of O2 cancel. Now I've got moles of zinc oxide on the top. I got to do one more step. 1 mole of, this looks terrible. You know what? I'm going to rewrite this. I'm going to turn my iPad sideways and I'm going to rewrite this. So bear with me 1 second. All right, maybe I'll do it this way. Get out of here. Okay. Sorry about that. All right, so we had 1.6 grams of O2. We had 32 grams of O2 for every 1 mole of O2. Wow, why is that being so bad? Let me put a finer pencil. That looks better. From the balanced equation, we had 3 mole of O2 for every 2 moles of zinc oxide. 1 mole of zinc oxide. Anybody got the mass for zinc oxide? You got your periodic tables handy? You can figure this out. I do not.
It's 81.39.
All right, one. Cedar, you got it?
Yeah, for zinc oxide, it's 81.39.
81.39. Can I get some agreement to that? Anyone else get that?
I got that.
All right, so we're going to say 81.39 grams of zinc oxide. And again, this is from the periodic table. You found zinc and oxygen, so 16 plus the mass of zinc must be somewhere in the neighborhood of 75, something like that, or 65. And you add it together and you get the mass of zinc oxide. So you can cancel out the moles of zinc oxide, the moles of oxygen, the grams of oxygen, and you will get grams of zinc oxide, right? So I could probably go back to this and we can see that. Same story, right? 1 over 32, 2 over 3, 80 to 2.71 grams of zinc oxide. So really, all the stuff we've been talking about really boils down to being able to do this sort of calculation using a balanced equation. I'll be honest with you guys, if you can master this kind of math, you'll be like 99% ready to jump into chemistry next semester, because this, this is the stuff that's really, really the hardest, I think, for students to get a grasp on. It's not that complicated. At first, it looks hard, but really, this is the bulk of it. But I want you to keep in mind that this is the most basic of this kind of problem, where I give you mass of something and you calculate mass of something else. Think of how this could be more complicated. Oxygen is a gas. Do you think in real life we would measure oxygen, which is a gas, by measuring its mass? What do you think? Chris, you're shaking your head no. How would we measure amount of oxygen?
Volume?
Probably volume, right? Because that's the easiest thing to measure for gases is volume. So if I gave you a volume of gas, right? Now all of a sudden we're thinking about gas laws. Is just giving the volume of oxygen enough for you to know how many moles of oxygen you had?
No.
No, it's not, because remember what else we had to deal with? We had
Pressure.
PV equals nRT. So if you wanted to know the amount of gas you had, I would have to give you pressure, volume, R and T. Then you could find moles of gas. And once you knew moles of gas, you could calculate moles of one gas. You could calculate moles of oxygen and change it into moles of zinc oxide. And then you could change moles to grams. So even though the problems look relatively straightforward, there's a lot of subtleties based on how you're given individual substances, right? So in this particular case, another way you could have stated this problem is you could have said something like, how many grams of zinc oxide can be produced from 100 milliliters of oxygen at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius, right? So that adds another layer of complexity to the problem. So that's, can you do a gas law problem, right? So it's checking, can you do a gas law problem? Then can you do a stoichiometry problem, right? And those are legitimate questions, right? Those are questions that chemists deal with every day. We don't just make these up to make your life complicated. For a quiz, I would not ask you a complicated question like that, all right? A quiz, I might say, you know, if you've got 15 milliliters of oxygen or 15 liters of oxygen at 25 degrees and 1 atmosphere pressure, how many moles is that, right? I might ask you that. Or I might ask you how many grams is that or something to that nature. I'd keep it a simple step. But on an exam, I might make it more complicated, but I would line it up or I would give you steps so that you could figure it out stepwise, right? Because again, this class is about mastering techniques and then being able to use them in unknown situations. It's not about mastering everything you're going to get in the next class, all right? So here's another simple kind of mass problem. I know the answer is there because I'm not showing it as a PowerPoint slide. If I went to the slideshow and just did this as a slideshow, maybe the answer would go away. All right. So here's a question for you guys to think about. If you want to try this, how many grams of CO2 gas are produced from the reaction of 1 gram of sodium carbonate with that excess acetic acid? So first thing you do have to do is write the balanced equation, right? At this point, I would not expect you to be able to write this balanced equation. I would not do that. I would give you this balanced equation, right? So here's what you're going to end up with. How many grams of CO2, how much of this can you get from this? So if you didn't have a chance to see that or you don't have the PowerPoints up, maybe you can take a minute. Trying to see what time it is here. It is
6:46.
6:46. So we still got time. So why don't you guys all take a minute to work on that, and I will do the same on my iPad here, even though I know the answer is right there in front of me. I'm going to write it out and try to solve this. So go ahead and try this guy. I'm just curious how many people are in class right now. It doesn't matter. Okay. My numbers might not match yours because I'm doing the periodic table from my head. So I might not have the same number of sig figs. Just looking at who's all in the class. Looks like almost everyone's here, but you guys are being really quiet. Only a few of you are answering questions. I need to start calling on people. I haven't harassed Min Sung yet today. What up with that? Min Sung, what's going on?
Hi.
How you doing?
Very good.
Yeah, Rudvij, what's going on, man? He's ignoring me.
It's going pretty good.
All right, there you go. Is you sitting next to Brian?
Not today.
Brian, you out there?
Yeah, I'm here.
You're here. Oh, all right. Who else can I pick on? Let's see. Cindy, I heard her talk earlier. Brennan's there. Raul's there. Raul, how's basketball? You still finding some time to play?
Yeah, I'm still working. You know, I'm
Are
still
you?
grinding.
You
Yes,
are.
sir.
Is the team still playing, or are you just playing on your own?
Oh no, yeah, no, our tournament got canceled, so we're all done.
You're
But
done.
I'm still working out. Yeah, we're done.
You're working out like at the gym, or are you actually playing basketball?
Oh, I don't really we can't really go anywhere to play pickup, or so I just kind of work out of my house with basketball drills and stuff.
Man, oh man,
It's rough, but it's all
Are
right.
are you living on campus, or are you close by? What's going on?
I'm close by, so it's fine. It's not that far.
Yeah,
But yeah.
You could be playing like John Madden football or something, right?
No, I'm just getting ready for next season though.
Are you? Are you?
Yeah.
Oh, that's interesting. Joan, the quiet one, how are you? Oh, Joan.
Hi, I'm good.
You are? What are you up to? What are you filling your days with?
I've been doing a lot of yoga and eating. It's kind of bad.
Eating is a popular pastime, I think. A lot of people get into that.
Yeah. Well, I mean, if you're stuck at home, you kind of.
Yeah, I've been baking bread. My wife made some jam. It's not pretty, but I am not sitting in my house. I'm still running every other day and working out. I gotta get out. It drive me crazy because I spend 3-4 hours a day on Zoom meetings, and honestly, we talk about the same thing every day. Nothing changes, so it's kind of problematic. But I don't know. Atria, what are you doing?
Hello, not much. I just walk my dog every day, but like yesterday we got attacked by a pit bull, so that was fun.
That doesn't sound like fun to me.
Yeah, he ran away from his yard. I don't know, but I like turned into Kung Fu Panda and I started like kicking it, but we're fine.
That's funny. Rosa, what are you doing? Are you and Sarah hanging out together virtually?
Not right now.
No?
No.
I thought you guys were like best buds.
Oh, we are, but
Oh.
we know each other.
That's good. You don't want to get anything from her. Nick, what are you up to? Nick Tran, come on, don't be shy. What have you been up to? I see you there, Nicholas. There you go.
Just chilling.
Yeah.
Practice, just practice.
Yeah.
Yeah.
Well, it's good. I'm glad you guys aren't like spending your whole time working on school stuff, are you?
I'm just doing school stuff.
Okay. Oh, of course you are. Now you're talking to everybody. You got to be like, oh, I'm the super student, right? Daniela, what's going on with you? You're not hanging out with Andrew. Are you like FaceTiming every day?
Yeah, we're FaceTiming for the most part. We saw each other once.
Yeah, that's too much.
I know.
You can't get his grandma sick. You don't want to be the one that be responsible for that.
I know. That's why he came over to my house.
He could have brought it back to her.
True, but I'm not sick.
All right. Did anyone get an answer for the problem? Anyone want to share their answer?
I did.
All right. What did you get?
I got 0.415 grams of CO2.
Did anyone else get that?
No.
Okay, that's an answer. Did anyone else get an answer?
I got 2.71 grams of zinc oxide.
Wait, zinc oxide? We were working on carbon dioxide.
Never mind then.
Never mind. All right, anyone else? You want to share? You want to take the computer screen? Want me to hand over the screen to you? Anyone? All right, I'm going to go back to my iPad. And let's see, anybody got their hands up? No hands up. All right, let's go back to share screen. Let's go back to iPad via cable. Share. Come on. You can do it. All right. So I may have written something down incorrectly. So let me just make sure I got this. Na2CO3 plus 2CH3COOH goes to 2NaCH3COO plus CO2 plus H2O and 1 gram. So here's how I started. I started with 1 gram of sodium carbonate, Na2CO3, right? I did that right. I added these things up. I believe sodium is approximately 23. So 23 times 2 is 46 plus 12, 46, 58. Oh, I did it wrong. I can't do math. I thought I did this on my calculator and I still did it wrong. So 23 times 2 is 46 plus 12 plus 16 times 3 is 106. Oh my gosh. Y'all see where I made my mistake there? But see how easy it is to fix on the iPad? Look at that. 106. Did anyone else get 106 grams for sodium carbonate?
Yes, I got 105.991.
Yeah, I didn't. I just tried to remember the numbers from my head. Okay. Then from the balanced equation, you should be able to see from the balanced equation for every 1 sodium carbonate, there's not a 1 sitting, but there's a 1 there. You have how many carbon dioxides? What's the ratio between sodium carbonate and carbon dioxide? You can see it right here. What is the ratio?
It's 1 to 1.
It's absolutely 1 to 1. And then we just have to get the molar mass of carbon dioxide. 12 plus 32 is 44. Of course, now I can go back and do my math over again. Oh my gosh, my calculator's not happy. 1 divided by 106 times 44 is 0.415. So I don't remember who yielded their 0.415 answer, but it was right. Who was that? Somebody take credit.
It was me, Cindy.
Yay, Cindy, 0.415 grams of CO2. So if we go back to the PowerPoint slide, you will see, there it is, 0.415 grams of CO2. So again, a very, very straightforward kind of question where you're asked one thing, how many grams of this? But if we look at it a little bit, you'll notice that, the wording is a little interesting. How many grams of this are produced from the reaction of 1 of this with excess acetic acid. So now they're telling you in the problem, you got a whole bunch of this stuff. We're not concerned about it. It's excess. So when you see that word, you can just ignore that substance, because I don't know how much of this acetic acid stuff I have. I just know that I have way more than I need. All right. So what are other questions you could be asked for this particular problem given numbers? Well, if you got 1 gram of this and you're asked about grams of CO2, but again, carbon dioxide is a gas, right? Am I going to ask you for the mass of a gas in real life? Probably not, right? So that might be where you have to make use of your gas laws, and you might be asked to change grams of carbon dioxide to moles, or I actually wouldn't ask you moles, maybe to a volume of carbon dioxide. All right. Okay, so I'm showing you this and you can look at it, but I'm not going to go through it because I hate spelling out these things for fear of you saying, oh, I just got to memorize how to do these things. And then that's always all I ever have to do. All right. What's better for you is to practice solving problems going from one substance to another, right? Start with one thing, end up with something else, right? It doesn't have to be on the opposite sides either. I could give you this and ask you this, right? So here's a ratio, 1 of this to 2 of this, or 2 of this to 2 of this, or 2 of this to 1 of this, or 2 of this to, there's like a whole bunch of ratios in this problem that you can write, all right? And you don't have to practice writing them, but understand that you can pair any 2 substances up that you want in the balanced equation. Once it's balanced, right, you got mole ratios for everybody. So you should be able to calculate any one of those particular problems. All right. Let's see, we got a few more minutes. So we can make your life more complicated. All right. So in real life, we don't mix together the right amounts. All right. So in this particular equation, it takes 1 of these for every 2 of these, right? But you'll notice that way we wrote this, I said, I gave you a whole bunch of extra for this, right? Anybody know why we use extra in real life? Why wouldn't I just say, well, the ratio is 1 to 2. Why don't I mix it as 1 to 2? That would make sense, right? You mix it as 1 to 2 because that's what the formula says. I should only mix 1 mole of this with 2 moles of that because I don't want to waste things. Well, in real life, chemical reactions are picky, and we have to force them many, many times to go the direction we want them to. And so oftentimes we'll use a whole bunch of extra of one thing to force the other guy to get used up, right? That happens all the time in chemistry. And what we end up with something called an excess limiting problem, all right? Where we have a certain amount of one substance and too much of another, and you have to decide, okay, how much product am I going to make, right? The key thing to remember is that once one of the reactants is used up, the reaction stops, all right? And we'll talk more about this in pictures if we start getting on to the next thing, all right? So if you look at this slide, all right, here's a pictorial, or you could say a molecular view of
It's
this.
still showing the iPad.
It's still showing the iPad. Thank you guys for not. All right. I'm sorry. I could see this thing on my screen, and thanks, Cedar, for telling me that. All right. Can you see it now? Can you hear me now? You can.
Yeah.
All right. So this is kind of a pictorial view of what's going on in a chemical reaction. And if you look at this, this is just the formation of water. So we're taking oxygen and we're reacting hydrogen and we're making water. But according to the balanced equation, I need 1 of these and 2 of these to make 2 of these. All right, 1 of these and 2 of these. But this particular case, I've got a whole bunch of extra oxygen. How do I know? Well, because it's left over here at the end, right? This is an example of an excess limiting problem. And again, you might be scratching your head and saying, why are you doing this to me? I don't, doesn't make any sense. The answer is, in real life, we almost always use excess to force a reaction to go to completion, right? So in this particular case, oxygen is abundant and it's cheap, and I want to make sure all of the hydrogen gets used up. So I use a lot of extra oxygen to make sure all this hydrogen gets used up, right? And if you look at the picture, right, you can kind of see that, all right, I know that I have to take 2 of these for every 1 of these. So 2 of these guys will be able to take care of 2 of them. These guys will be able to take care of the other 2, kind of the way they split up, right? So every 2 of these goes with 1 of these. These 2 go with this guy. These 2 can go with this one. These 2 can go with this one. These 3 here at the top are left over at the end of the reaction. They're excess, right? In real life, did these 2 react with this one? No, I don't. Nobody knows where they reacted with. It's just a picture to kind of help you understand that we dumped a lot of this stuff and some of this, and because there was so much more of this, all of this stuff got used up. So here's some terminology that you're going to want to be familiar with. This guy here is called the limiting reactant or the limiting reagent. It's the one that gets completely used in the reaction. This is called the excess reactant or the excess reagent, and it's the one that's left over after the reaction is completed. So here's a question for you. Which one of these, oxygen or hydrogen, decides how much product I get made? Does the oxygen tell me how much water I made, or does the hydrogen tell me how much water I made?
The hydrogen.
The hydrogen, right? So you just made a very important statement, and that is the limiting reactant always determines how much product you make, right? This guy always determines because, well, sorry about that. Because as soon as this is used up, the reaction stops, right? If you had said, well, I've got this oxygen, so I've got 1, 2, 3, 4, 5 moles of oxygen. The balanced equation says for every 1 mole of oxygen, you get 2 moles of water. If I had 5 of this, I'd predict I would make 10 moles of water. Did I make 10 moles of water? No, I made 4 moles of water. So clearly, this guy cannot be used to do any math. And that's important because in a little while, you're going to get into these problems called excess limiting, and they're going to give you amount of this and amount of this. And they're going to say, okay, how much of this can be formed? And you scratch your head and say, well, I don't know how much of that can be formed. And we're going to talk here about the easy ways to figure these problems out, because in reality, it's no more complicated than the problem you just did. You only have to do it twice, all right? We talked about this, so we're not going to worry about that. Okay. And I actually prefer not to do this problem either, because I'm never going to ask you a problem where the answer is moles. All right, so let's go on to one that's more gram based. All right, so let me close out this PowerPoint and go to this one. There'll be a little bit of review at the beginning of this one. I apologize. All right. Oh, sorry. I want to go to the, let me just get to this. So that, you know what? We don't need to see the full screen. We can just do it this way. All right. All right. So mass stoichiometry. This is just a practice problem where they're giving you one and asking you about another one. So this is not a limiting problem. I don't want to spend any of the remaining time. We only have a couple minutes left. All right. This is a classic. Don't look at the answer. Close your eyes. Close your eyes. Close your eyes. You probably already saw it. All right. Let me. The answer is still there. You can still see it. Whatever. And let me
You
go.
have to put it in presentation mode.
I know. You already saw the answer, so it's no fun anymore. The problem is I've got my view of all your faces right at the bottom, so I couldn't click that very quickly. All right. Pretend you didn't see anything. Nothing to see here. Moving along. La, la, la. All right. So here's a classic excess limiting kind of problem that you might run into. You got a balanced equation. Right? So no problem there. You don't have to worry about balancing it. I'm pretty sure it's balanced. So let's see. We've got 2 nitrogens, 4 hydrogens. Oh, it's not balanced, is it? 2 nitrogens here, 2 nitrogens here, 4 hydrogens here, 2 hydrogens. So it's not even balanced, okay? So that's another curveball that's being thrown at you, this question. But Oh, I'm sorry. This is actually not the one I wanted. This is not the excess limiting problem I wanted. There we go. This is the one I wanted. All right. So this is a limiting reactant problem where you're given the mass of substances and asking you how much product could be produced. All right. So let me write this down on my iPad. And if you guys want to write this down on a sheet of paper as well, we can walk through the solution to this particular problem. I'm going to write it down. I'm going to try to write it down. If my pen, turn the pen on. I'm learning, guys. It's taken me a long time. So we've got 20.0 grams of aluminum metal. So that's Al solid. Reacts with 25.0 grams of Cl2 gas. What is limiting in the mass of aluminum chloride? Okay, so I'm going to swap you guys over to my iPad. I don't see any hands raised. Come on, baby. Come on. Come on. Oh, yeah. Okay. All right. What's the first thing we got to do in order to figure out this problem? Can we do any stoichiometry in this problem without something?
We need to make a balanced equation.
Absolutely. We need to write a balanced equation. So I wrote these out already. They weren't written out for you. It said, if you go back to the reading of the problem, it said 20 grams of aluminum metal and 25 grams of chlorine. I don't even know if it said chlorine gas. It just said 25 grams of chlorine. And notice how I wrote this. I wrote aluminum as Al solid, and I wrote chlorine as Cl2 gas, right? So these are things that, while they look like tricks, they're just part of the learning curve for doing chemistry problems, right? I just want to remind you, I don't remember who helped me with this last time. How many of these things are there that come as pairs? You remember how many there are?
7.
7. So let me just remind you of them. H2, N2, Cl2, F2, Br2, I2, 1, 2, 3, 4, 5, 6. What's the other one? O2, right? So those are the ones that come as pairs in free elements. This is something you got to assimilate those guys, right? Those have to be in your brain. You need to know those. So when the problem says chlorine gas, you write Cl2 and not Cl. When it says oxygen gas, you write O2, all right? So those are the 7 that all come as pairs, and there's probably not going to be any super indication to you to write those, okay? So now it's saying you're going to react aluminum metal, I guess you can translate metal to solid, plus chlorine gas. And they don't even give you an equation, but you're smart. You recognize this as A plus B. Oh, that was kind of a poor choice of markers. You recognize this as A plus B goes to what? Help me out here. What does it go to? Anyone? A plus B goes to
AB.
AB, absolutely. Was that you, Nick?
Yes, sir.
That was Nick. Nick chimed in. Woohoo! So, all right, let's practice what we learned earlier today. Nick, you're still on the spot. What kind of reaction is this?
Ooh, single.
Nope. Starts with an S. You got the first letter right.
I have no clue.
Anyone want to help them out? It's a synthesis or composition. So this is a composition reaction where you're taking simple things and making more complicated things. So if I'm taking aluminum and chlorine, they told you the name of the compound. It's aluminum chloride. Anyone want to take a stab at the formula for aluminum chloride?
AlCl3.
Absolutely, AlCl3. And the way Cedar got that is she looked on the periodic table and saw that aluminum was in group 13, so it's basically +3, right? And chlorine is in group 7, it's -1. So you crisscross, and that's the formula you would get for aluminum chloride, all right? Now, again, many of you are looking at this and saying, oh, crap, I would never do that. Well, if you don't practice, you're not going to do that, right? You might write something like AlCl, or you might write something like AlCl2. Guess what? If you write this wrong, but you do everything else right, I'll give you the credit based on writing this incorrectly, right? You'll just lose a little bit of points for doing that wrong, but you're not going to get the perfect score, right? So if that's your goal in life, if you're the type A that always has to get everything right, make sure you can write the formula correctly, right, from the name. All right, is it balanced? Easy question. The answer is
No.
no. All right, so let's start over here. This one's actually a little more complicated. There's a 3 over here by the chlorine and a 2 over by this chlorine. So can I balance this by just putting one number in front of one of them?
Nope.
I could if I used a fraction, right? But if I want to use whole numbers only, I can't do that. So in order to balance this one, I'm going to put a 2 here and a 3 here. So I have 6 chlorines here and 6 chlorines here. So you got to find the least common multiple of both of those guys. Right?
And a 2 in front of Al.
Yep, we did. We're not quite done. Thank you. Yep, a 2 in front of Al. So now this equation is balanced. I've got 2 aluminums, 6 chlorines, 2 times 3 is 6 chlorines. All right, it's balanced, right? So when you first looked at the problem, you didn't see any of this stuff, right? Right? But that's inherent in how you have to solve the problem. And that's what you're going to run into all the time in these sorts of questions. They're not going to give you the balanced equation. They're not going to give you the completed equation. I know that seems wrong and unfair, but it's designed to force you to do a bunch of practice. However, in the homework on sapling, it gives you pieces of these so you can practice doing the little pieces before you have to do a more complicated problem. Although I get it, sapling will give you a wrong answer if you're off by a decimal point or something. And I think I limited it to a bazillion times of trying on those questions. So hopefully you won't lose points for trying multiple times. Okay, so the question now is, you got 20.0 grams of this stuff and 25.0 grams of this stuff. How much of that are you going to make? And you scratch your head and say, well, I don't know, because usually I just got one of these. You gave me one of these and said, how much of that do you get? Or you gave me this one and said, how much of that do you get? Right? So which of those are you going to do? The answer is both. No, I don't want to do both. Well, why would you do both of them? If you do the math based on aluminum, if you start at aluminum and calculate AlCl3, you're going to get some number of grams, right? True? If you start with chlorine and calculate this, you're going to get some number of grams. So this is an X and this is a Y. One of these answers is going to be right. It's either going to be this one or this one. Right? Now let's think about this logically. Each of these is going to result in some number of aluminum chloride being formed, assuming you used up all the other ones, right? It's just a number, it's just math, all right? One of these numbers is going to be bigger and one of these numbers is going to be smaller. Which one does logic tell you should be the right answer, the bigger number or the smaller number? Remember, the reaction stops when the limiting reactant runs out. So without thinking too hard, should it be the bigger number or the smaller number?
The smaller number?
It's the smaller number, right? And this is, again, this is another case where as an instructor, I feel like I'm doing a slight disservice, but I'm telling you that understanding excess limiting completely is really hard. Getting your head around it so you always know what's going on is hard. So this is an example where you just want to do the problem and follow the rules. So the simplest way to do excess limiting is to take each starting material and calculate how much product you get. Take the next starting material, calculate how much product you get. You're going to get a number of products. The answer, the correct answer, is the smallest number, right? That's always how it's done. All right, so we got time. Let's go ahead and solve this particular problem. I made a mess of my page. So let me go to eraser and let me see if I can get a little bit of room here to solve this problem. I love how this works. This is way better than writing on the whiteboard, sort of. All right. Okay. Let me erase this because this is unimportant right now. And let me erase this because I'm going to need a little bit of room to write on this. Okay. So let's start with aluminum. I have 20 grams of aluminum. How many grams of aluminum in 1 mole? I don't have this number memorized. Has somebody got their periodic table handy?
26.98.
So 26.98 grams of aluminum is 1 mole of aluminum. I got the fine pen. The balanced equation says that there are 2 moles of aluminum for every 2 moles of AlCl3. Okay, I can do this one on in myself. So you said aluminum is 26.98. So 26.98 is aluminum plus chlorine is 35.45. 35.45 times 3. So aluminum chloride is 133. Oh, sorry about that. 1 mole of AlCl3 is 133.33 grams of AlCl3. So I'm not going to do the math yet. That's just going to get me grams of aluminum chloride if I started with aluminum. And there's an assumption here that you guys need to understand. When I do this, I'm assuming I have enough chlorine to react with all this aluminum. I don't know if I do. I'm just assuming I do. That's the assumption in this problem. When I start with chlorine, I'm assuming I have enough aluminum. So 25.0 grams of Cl2, 1 mole of Cl2 is 35.45 times 2. 70.9. Then we know from the balanced equation that there are 3 moles of Cl2 for every 2 moles of AlCl3. And then the same is true for the molar mass. 1 mole of AlCl3 is 133.33 grams of AlCl3. Now, before we do any math, I got a question for you guys. All of the problems I've done on this page are grams of something to grams of something else. How many steps does that take?
3.
That's something that should get into your brains through assimilation. If you're changing grams of one thing to grams of something else, it pretty much always takes 3 steps, right? What's the first step? Always change to
moles.
Change to moles, right? Where does the second step always come from?
The formula?
Well, where did this 2 to 3 ratio come from? Where did this
Changing from the moles of one to the moles of
Right,
another.
right, but where did that ratio come from? I didn't just make it up out of thin air. It always comes
From the balanced equation.
Absolutely. The middle step always comes from the balanced equation. And then this last step, same story, changing moles back to grams, right? It's no coincidence these problems all look the same, right? Right? So if you do enough of them, again, it's not a matter of understanding. As much as I want you to understand this, you can do this without having any idea. I hate to say this, but you can do these problems without having any clue as to what you're doing, right? It's true, right? I'm sorry to say it's true. All right, so let's do the math on the top one. That's 20.0, I think. I lost a sig fig there. I'm not too worried about sig figs right now because of this silly iPad. So 20 divided by 26 point, wait, stop. Do you have a gut feeling for which one of these is going to give you a smaller number?
Aluminum.
Pardon?
Aluminum.
Well, let's look at this. There's 3 moles of chlorine for 2 moles. This really looks crappy over here. So I've got 20 grams of aluminum, and it's light, right? Aluminum is light compared to chlorine. Aluminum's only 27, chlorine's 71. So just by looking at this, I'm taking about the same number. Here I'm dividing by 27. Here I'm dividing by 70. So this first step, chlorine is a lot smaller than aluminum. Here I've got a ratio of 2 to 1. Here I've got a ratio of 2 to 2, so 1 to 1. Here I've got a ratio of 2 to 3, right? So I'm dividing by a bigger number. I have a feeling that this is going to be the answer because this guy, it looks like I'm starting with a lot smaller moles of chlorine. Even though I have a bigger number of grams, I have a smaller number of moles. And that was kind of one of the questions that was, I think, on the last exam. Right? Rank these by, or which one of these has the smallest number of moles, right? So that's not something I'm going to ask you to do, but it's always useful to have it in your head when you're doing a problem beforehand to think, I wonder which one of these is going to be the right answer. So 20 divided by 26.98 times 2 divided by 2, I'm not going to do that, times 133.33. All right, so for this one, that seems odd. Did I do this right? Well, I'm just going to write it down. The answer comes out to be, this is the math that my calculator gave me. Not sure why. I don't like it, but it's 98.83.
That's what I got.
Oh, good. And that should bother me. Why does this number bother me? Because I've got 20 grams of aluminum and 25 grams of chlorine. If I put all of it together, what's the most I can make? 20 plus 25 is, don't all say it at once. 20 plus 45, right? This is 98 grams. Can I make 98 grams if I start with 45 grams of stuff? No, it's not going to happen. All right, let's try the second one. All right, I'm going to try the second one. I'm sure you already all have it done. 25 divided by 70.9 times 2 divided by 3 times 133.33. And I get 31.34. Anyone else get that?
Yes.
31.34 grams. All right. So this is a classic example of an excess limiting problem where you're given amounts of 2 starting materials, this guy, and you're asked how much product can you make? All right. You got to do them both. There are other ways to solve this problem, right? So when you read the book and you look through practice, there are other ways to solve this problem. And if you use a different way, that's totally cool with me. There's actually like 3 different ways to solve this problem. I'm not going to go through all 3 ways because I don't want to confuse you. If, however, you use a different method and you get the right answer, perfectly acceptable with me. Okay, does that make sense, you guys? Other ways, right? One other way is to start with one and see how much of the other you need, all right? That's one, and you can see, oh, do I have enough? Yes. That means that's the excess in that one. If I don't have enough, then it's the other one, right? There's a lot of different ways to do this. You can do it with percent composition. You can do it with moles, a lot of different ways. But I don't want to make it so that you have to learn every single way. If you want to find a different way that's more practical for you, that's totally good. All right, it's 7:27. Let's go back to the PowerPoint and actually see if we got the answer they wanted us to have. I stopped sharing my screen. Let's go back to the PowerPoint and we write that, we do that. There's the mole relationships, right? They're actually doing it a different way in the slides, but that's the answer, 31.3. That's what we got. If you look at, I'm sharing this with you, right? You guys can see the PowerPoint?
We
No.
No.
I'm sorry. Let me share my screen again. I'm totally not doing this well. Zoom, go back to my Zoom window. There we go. Share screen. I forgot. All right, so there you have it. So if you look at the way it was solved on the PowerPoint, what we did here is we actually calculated how many moles of each of these we had. So 20 grams of aluminum is 0.741 moles. 25 grams of chlorine is 0.353. And then if you do the mole ratio, you need 2 to 2. So this is 0.371 and this is 0.118. So that means this is the limiting. There's much smaller amount of that. That is yet another way. I don't like that method as much because I don't think it's obvious, right? I prefer to do a method that's slightly more obvious than this. All right, so we're pretty much out of time. There's a couple of topics left. Percent yield, well, we actually have a few minutes. Can you bear with me to cover this last topic? No, let us go. We're sick of this. Let us go. It'll only take a minute. All right. One last thing related to this is something called, come on. It's called percent yield, okay? And so in a chemical reaction, you don't always get what you expect, right? Is it a Rolling Stones song? You can't always get what you want. In a real chemical reaction, most of the time they never go to completion and you get byproducts and all sorts of other things happen, right? And so you never really get what you're supposed to get. However, if you do the math based on the reaction, so the math we just did right here, this number right here, 31.3, that's how many grams you expect based on the math. That's called the actual yield, right? That's how much, based on the starting materials, everything goes like it should, I expect to get 31.3 grams. In real life, am I going to get 31.3? I'm going to get something less than 31.3 because it's other stuff's going to be formed. And so there's this thing called percent yield, right? So the theoretical or actual yield is the amount it's supposed to be, and that's based on the stoichiometry. The actual yield is what you get, right? And it's always less than the theoretical yield. And you just put those two to make a ratio, so the actual over the theoretical. So in the previous problem, we were supposed to get 31. If we got 30, our percent would be 30 over 31 times 100, or something like 90%, right? It's really a straightforward statement, and there's really no complicated math, right? So we don't need to go through all the math in order to calculate this, but saying you've got 68.5 grams of this, kilograms, oh man, they made it really complicated by going to, well, it's still grams to grams, right? But they're saying you should have gotten 7.84 times 10 to the fourth grams based on the math of the problem. But here they say this is what you really got, right? So here's the actual yield. It makes this, right? You have to calculate this number. This is what the math tells you. So if you put the actual over the theoretical, you get the percent, 45%. It's really straightforward math. But it's a common thing. This is not the most important topic in this chapter. The most important thing is, can you write a balanced equation? Can you go from amount of starting material to amount of product? That's really the most important. Excess limiting is related to that. It's important, but it's not the most important thing. But they're all brewed together in terms of, can you do stoichiometry calculations. Okay, I'm going to stop right there so I can see all your smiley faces again. Before I bail out of here, do you have any questions for me about what's going on? You all know you have spring break for a week, right? Yeah, so the next week, starting Monday, is spring break. I'll be around, so if you guys email or have a question or something, if you want to do a Zoom office hour, just let me know. I'll be happy to answer questions. I'm not going anywhere. I'm not demanding that you work on anything, but you know, if you're bored and you got nothing to do, you probably should be doing some of the homework that's found in Sapling, which will give you practice, and also look through those sheets that are posted on the Titanium website. Marlo, send me an email to remind me of the ones that I have to post answers for. And then I already forgot. So somebody maybe remind me what the name of that, was it EndNote? That wasn't it. It was something else. I forgot already.
Notability?
What was that? Notability?
Yeah, I sent you an email.
Okay, perfect. All right. So that's it. Nice seeing you guys. Hope you have an awesome spring break. Stay healthy. Get out there, get exercise, eat yummy food.
I have one question. So
Yes.
So basically, are we gonna post a video again for today's lecture?
Absolutely. Yep. This video got recorded. This lecture got recorded. So as soon as it's processed, I will post it on YouTube and send you a link to it.
And what about our quiz? Is it gonna be like Drew Sapling?
No, but I think probably what I'm going to do is what I mentioned earlier. Maybe you weren't here at the time. What I'm going to do is I am going to write the quiz like as a Word document, like 5 minutes before the class starts on Thursday. And I'll explain more about this on the next Tuesday we meet. I'll post it on Sapling so you can download it, print it, do it, and then just take a picture of it and send it back to me. And if you can't print it, you should be able to download it save it as a PDF, and then just use your finger or a stylus or something to write it. Or you could even just look at it and type your answers on another Word document. I want to make this as easy as possible so that everybody can access the quiz. And I realize that it's probably going to take longer because you won't necessarily be able to handwrite things. So, I mean, this is a learning experience for me. I want to make sure that you have every opportunity, all of you, to take that quiz and feel comfortable taking it. Does that make sense?
So then when would the quiz be?
The quiz is likely to be the Thursday after we get back from spring break.
And then the exam would be that same day too, or?
No. The exam would the earliest the exam would be the following Thursday, a week later. Okay. But I suspect I'm going to postpone it a little bit because we lost a week to nobody doing anything. And I kind of feel like there's a little bit of a lag with this new technology of learning. I really just want to make sure you guys are comfortable with this material. So we'll go by ear. If you guys feel comfortable, we can take it a week after the quiz. If not, we'll postpone it a little bit longer. That seem legit to you guys?
Yeah. Yes.
All right. I don't see any other hands raised for questions. It's awesome seeing you guys. Some of you don't have your cameras on. That's not fair. I want to see all your faces, but maybe next time. I don't know. All right. Take care, guys. See you in a couple of weeks.
Yeah. Professor, have a good break.
Bye. All right.
See you later, Professor.
Bye, guys.
Bye.